5 seconds early. We'll do it. So thanks for coming in, guys. I hope you're all on the right talk. Event-driven architectures enabling microservices. So that's what we're here to talk about. Basically, what we're going to talk about is if you have a monolith, which I'm sure none of you have, but should you, in theory, have a monolith that you wanted to convert it, how do we do that? How do we get it over in microservices? All these great buzzwords we're hearing, microservices, serverless, all this fun stuff that's going to solve all our problems. How do we get there? So that's what we're going to be talking about today. But first, my marketing person says I have to talk about myself. So who am I? I'm a .NET architect and developer. I've been building for years. And this is my book. I wrote it, How to Reengineer .NET, basically taking legacy software, injecting new architecture, dependency injection, services, repositories, all that good stuff. Injecting that into a legacy system that typically doesn't have anything, web forms that just talks directly to the database, those kind of things, ADO, straight ADO. Wrote a book on that a while ago. I help retail and finance do that very thing. Those are my verticals of retail and finance. So we take legacy applications like order management systems, things like that, financial systems, inject all this good stuff, all the good technology in it to make it something that will grow. Slides will be on SlideShare, so don't worry about it. You can take pictures if you want, help yourself. But you don't have to because they will be on SlideShare, so you can grab them there. So before we start, let's talk about exactly what is event-driven architecture. If you look around on the web, you Google around, you'll find a lot of definitions of it. And this from TechTarget is one of the most common. Basically, it's saying, well, you can read it there. An event is an identifiable occurrence that has significance for system hardware or software. So the events that they're talking about are more along the lines of, remember those old WinForms applications you used to build where you push a button and you define an event handler that would handle that button push event? Remember those days? Those are the kind of events that you typically find, and they take that event idea and move it into servers and web. So, but really what we need to do is distinguish between that type of event and a message. They're very similar, but there's a real distinction there, and we need to talk about that first before we can go any further. So first of all, let's talk about what a message is. A message requests an action to be performed. That's basically your button push, right? Your event that you have your event handler. That's really a message in today's parlance. So it requests an action to be performed. That action has not been performed yet. We haven't done anything. It's short-lived. Once the message is processed, you typically toss it. I mean, you can archive it, but it's rare that you really need something like that. It's got the full data payload. Everything that's necessary to execute that action, to do the thing that the message is requesting, is usually in the payload. So you can do everything you need right there. Since the messages are thrown away, you can only start processing right now. You can't go back in time. So if you want to start processing messages, you can add an event or an event handler, message handler, and start going, but you can't go back in time. And the basic idea is there's an expectation that something is going to handle this message. So whoever creates the message, they're going to throw it out there, and they're going to assume something's out there to handle it and do something with it, because this is a request for something to happen, right? And so somebody has to do that thing. Somebody has to perform the request. So let's contrast this with events. So events, they reflect an action that's already been done. This is a completed action. So the message said, please do it. The event says, okay, done. These are typically medium to long-lived, which means hours is fairly short. Usually it's days. Sometimes it can be years. I know Target in their EDA architecture, they keep, last I heard, they had about 6 years of events all saved up. Every event that ever happened at Target for the last 6 years, the thing is huge. They use Kafka, by the way. We'll talk about specific technology solutions later on the talk. But yeah, so they could be medium or long-lived, but they're around for a while. They typically have a partial data load or partial data payload, say that times 5 times S, which means that you only put in the data fields that changed. You don't put in, like if you're changing a customer record, you don't put in the whole customer. You put in their new name, whatever's changed. So it's only the delta. And historical events can be consumed. Since they're around for a while, they're around for a week, 2 weeks, you can go back in time and capture an event, process an event that happened 2 days ago. Messages, you can't, they're gone. But the basic idea is that there's no expectation that any of these events has a listener. So you can throw it out there, and you typically do. You throw it out there without regard to whether anybody's listening, anybody's going to do anything with it. This is just a repository for things that have changed. Okay, so let's keep that difference in mind as we go forward, because a lot of things that we're talking about are events, and people get those confused with messages. So let's talk about first what a message-driven architecture is. So state change, like we just talked about, state change is initiated by one of these messages, and it results in a state change. Please update customer last name. Results in a state change. Application components can communicate with messages. You know, once one component tells something else that it wants something done, again, we throw away the messages, and they're destroyed once they're processed. An event-driven architecture, they show that the state of something has already changed and been persisted. So, and every time a state changes, we put a new event out there. So we have a constant record of everything that's changed since the beginning of time. If you want to know everything that's ever happened in your system forever, and the order that it happened, you can go back to the beginning of your event source. Your event store, and come on forward. I don't want to confuse everybody. I misspoke and said event source. That's a totally different technology. So let's not get these mixed up. Event sourcing is very different than what we're going to be talking about here. So let's see an example. To set up our examples, what we're going to do is we're going to talk about a retail system. So you're online, you're on Amazon, you want to buy a red t-shirt. So what you're going to do is you interact with UI here, and you're going to update an order. I want my t-shirt. You hit the button, purchase. It's going to create an order. This is very simplified, right? But this is generally what we're going to be talking about. So we create a new order. We check inventory, make sure there are t-shirts available. We charge the card. First, we ensure credits available. If anybody's had experience in retail, you usually do charge cards in several steps. First, you reserve those funds, and then later on, you actually capture the funds. So it's usually a two-step process. So we're going to ensure credits available and then capture our funds. We decrement inventory. So we make sure that we remove them from our inventory record so nobody else is, so we're not selling the same t-shirt twice. We ship, we got fulfillment going on here, and then we tell the user, you know, your shirt is on the way. So this is the process that we're going to be going over in our examples. In a typical non-EDA architecture, so this is web forms. This is what we're building today. We'll start out with our actor over here. And this is not actor pattern. I should have renamed that. That's user. But so forget actor pattern. Forget event sourcing. Forget actor pattern. Forget everything else except what I'm talking about right here. So we've got our user here. They interact with the UI layer, and they create an order. And we have a bunch of our internal services. This is a big monolith. We have a bunch of our internal services that we create an order. We check inventory. We charge the card, everything that we just talked about. And all this gets saved to the DB. So this is what we're doing right now. We even have an external inventory system. So we ping that via an API. Say, hey, do you have any shirts? Yes, we do. Okay. And so then later on we say, hey, I want one of those shirts. Decrement. Okay, thanks. And then we write to the DB. This is how we're building things today. So basically, you can kind of, and Chris Richardson just had a talk, and he was saying that it's okay to build microservices, and I want to echo that. Okay to build monoliths. And I want to echo that. It is okay to build monoliths. That's a good start. You know, when you've got 5 users, including your mom and your grandma on your system, you don't need a whole bunch of microservices to handle the throughput. A monolith is okay. But you have to build the monolith so that we can later, when you've got 10 million users, we can start moving that to microservices and handle the throughput, okay? So this is basically when we're first getting started. So our app is a little baby, and it's now grown up. And now how do we deal with it growing up and needing to handle more throughput? So that's where we come in. So what's wrong with this architecture? Why bother? Let's just stick with our monolith. I mean, we got 3 of them going, right? So we got 3 of them going in here. We can scale. What's wrong with this? This is synchronous by default. So when you're a developer, you're banging out this code, you're writing all these things, you've got your controller on the UI that's calling these different services, say, order, service, create order, inventory service, check order, card service, charge card. This is all synchronous. Unless you go out of your way and create async code, all of this is going to be synchronous. That's, we all know that's a bad thing. You got to scale the entire app. What if only inventory check was getting really hot? There's a ton of action going through there. Everything's slowing down because everything's backing up behind inventory. How do you scale? You scale that whole thing. You got to scale the whole thing. That's bad. We want to get away from that. Unhandled exceptions can bring everything down. So if we're in here, we're trying to notify the user. We've done everything. We've created an order. We've charged the card. We've sent it to fulfillment. Everything's going great. We're about to earn $10 on our T-shirt. We try and send the user an email, and we crash. What goes down? The whole thing, right? So the user gets an error saying, I'm sorry, something went wrong. Big smiley face. Please try again. So what do? They go in there, and they enter the whole thing again. Well, they've already got a T-shirt. Now they got 2 T-shirts. So your user's upset. So on failure, user must manually resubmit change, and this also results in potentially unknown state. If we failed here, everything's already processed. If we failed here, we've got an order, but we don't know if inventory is yet. We don't know where we failed. So our DB is now in an unknown state. And there's no record of how we got here. So we can't go back and trace and see where everything fell off. So what we can do, this is how we start our migration path. We introduce just an event store, just for today. This is easily like a half a sprint thing. That's a 2-day thing. We introduce an event store. All we do is we add our order created event to the event store. For now, we'll talk about technology later, but for now, event store, just imagine it as a big write once database. So you're allowed to write a row and then read that row, but you can never ever change it. It's like a log. You can really picture it as a database log. So once you write it, it's done. That's cast in stone. So we have a little service in here after we've created our order. We write to our event store, and then we happily keep cruising along. No change, right? You'd be comfortable putting this into production as long as we know our event store is out there and available. This is fine. We can put this into prod. What have we done? What's the advantage here? What we've really done, this is the key. What we've really done is we've broken this thing out. So now that we have things in an event store, now all this stuff that really does not have to be synchronous, it can be async. All we have to do, so our users up here say, give me a shirt. It comes through here. We create an order. We write our event store. We return to the user and say, done. Your shirt's on the way. Okay? He's happy. I mean, that took 2 seconds less than it did yesterday. So our user's ecstatic. Great, my T-shirt's on the way. Meanwhile, behind the scenes, we've written this out. And now these guys over here, say you've got one application here. He subscribes to the event store and says, order created. Okay, great. Order's created. Let me go out and check my inventory. I'm going to charge the card. I'm going to decrement inventory. I'm going to notify the user. Everything happens exactly the way it did before, but our user's happy. We've got a solid record of what happened, and all this is time insensitive. Does it matter? I mean, when we were here, this stuff had to be fast, right? Fast, because we want to get back to the user and tell them everything's okay. This can take 10 seconds, 15 seconds, who cares? Yeah.
But you can run into trouble. Suppose they enter the credit card number wrong, and fix it.
Exactly, and that's, we're going to talk about eventual consistency in here in just a second, but that's a good point. But this all, assuming happy path. So let's just assume happy path. We come in here, we got our event store, we come through here, we process everything, we send our email to the user, we're checking inventory, and here, notice we can break this out into a separate DB if we want. We can write to the original DB since we're migrating. A lot of times as you're migrating, you gotta break the rules a little bit along the way. You know, the end result, you want it to be the way it really needs to be, but you can't get there in one step. So sometimes you gotta roll into production things that are breaking the rules and then slowly fix those rules as you go. So this could be one of the rules that you break, is this domain layer actually talks to that DB, whereas eventually we wanna go here. But you can see, we've just now separated all this stuff out. So now we've got this in its own little microservice. We've got 3 of them here. So we're processing away, and everything's happy. So this is a better approach, right? All we've really done is introduced an event store, and then had this start up, this process starts in response to a subscription. Everybody with me? Yeah.
So what I'm curious about is you've got like 2 separate domain layers. Potentially they're talking to the same database, potentially they're talking to 2 separate databases. I guess I'm kind of wondering as far as like for the original domain layer, whether that's going to be like a full mirror of the schema as well as the data included with the new migrated app, or are we looking at something where it would just contain the event stored data and also like the orders that were created and then kind of something else migrated off as well?
So basically, how do you separate out those database structures? Right. Yeah, so the question was, if we've got 2 DBs here, and we're migrating everything over, do these DBs have to be mirror images of each other? It depends on where you are in the migration. I mean, typically, the easiest way to do this is to just have this guy talk to this DB here. Maybe what you do is you move the tables that are specific to the order into a different schema. I'm a Microsoft guy, so I'll talk a lot of T-SQL and Microsoft SQL, but you know, Oracle and the others, they have similar ideas. So what you might want to do if you really want to separate, you start to tease apart your database, is you move your orders into a different schema. So you have to specifically say order schema dot table name, you know, query, update, whatever. And so that's kind of getting to the point where it's a separate database. You're starting to get those lines. You're starting to pull things apart. So initially, when you're at this point, this would typically be, I mean, I should have drawn this arrow here. Typically, you would be still talking to this DB. The long-term goal is to have a separate one down here. Does that answer your question? Okay. So let's take this the next step. Why don't we break all of these guys out into microservices? Everybody's writing to the event store. So he creates an order, he writes it there. We check our inventory system, we write an event, inventory assigned. So we reserve it, right? The financial system hits the card. We create an event, order amount reserved. Then we come back to inventory. This is where fulfillment lives. Fulfillment ships the item, item shipped. Then we hit the card. We actually grab the funds, you know, order funded. Then we go here, send the email, email sent. Now we know the whole process is done. So now all this stuff is all little microservices all running around in their own world. We can scale these however we want. And the only thing we've done, well, only, you know, there's things that have to be done in the side, right? But the only real architectural level thing we've done is introduce an event store. So this is the way that you slowly get to microservices. You don't have to rewrite your monolith in microservices and then flip that big switch, you know, and a year from now and cross your fingers and hope everything works. You can slowly, sprint by sprint, you can start introducing this. I mean, you can do this part here, right, and just ignore it. Ignore the event store. So one sprint, you put in the code here to write to the event store, and you don't do anything with it. You just let it sit there. You let that run for maybe a sprint 2, something like that. Make sure it's working in production. Everybody's happy if you're nervous about this. So you get there. You know, the NetOps gets accustomed to running this stuff, making sure they know that it's up and running. Everybody's confident. And then the next step is you introduce this subscription. Yeah. Okay, so the question is, when you write to the event store here, is it synchronous? In general, so this is one place where the diagrams were kind of split between where the eventual goal and where we are right now, because we're in migration, right? We're taking our first step towards where we want to be. This arrow here is the eventual target. We want the app layer to eventually be writing to the event store, and then later we write to the DB layer. That's because once everything's in place and we're fully converted over to event store, this is now our system of record. So anything that happened, this is it. Before, when we're here, this is our system of record. So we have to trust the DB. If DB says it's true, it's true. Once we get fully on event store, if the event store says it's true, it's true. If these two disagree, event store wins. So to get back to your question, if you need it to be distributed, that eventually, no, there's a single write here to the event store, and then there's a write to the database. If this part fails, there are strategies to come back later and fix the DB because you've already got your stuff stored. This is your event. I'll get to you in just a second. Let me finish this. This is your system of record. As we're processing what happened, as we're migrating, what we really need to do is this arrow needs to come down here instead. And this is a distributed transaction. I know that's an ugly word. We don't like to do that if we can avoid it. But what we have to do is in the process, while we're migrating, we actually have two systems of record. For the meantime, we believe the DB. If the two disagree, we believe the DB. We think we probably have a bug. We haven't written to the event store when we need to. Eventually, at some point during this migration, we change and we say, okay, event store is now our system of record. Now it wins. And so in that process, you have to have a two-phase commit. You have to write to the DB. If that's successful, you write to the event store, and then you return. And you do that all in a DB transaction. So if your transaction fails, if your event store write fails, then you kill the transaction. You don't commit it, and everything goes back. So we keep those two in sync. So that's a fairly short term, small number of months, 3 months, 4 months, something like that you have to have a dual commit, and then you can go to only committing here. Does that answer your question? Okay. Yes? No. The question was, is the event store using the DB? Is that it?
Not necessarily this DB, its own DB, otherwise how you survive a power cycle.
Okay, how do you...
All the system all application crash. If you use data store record as the only reliable reference, override the DB below, and that guy cannot survive.
Okay, the event store is totally different technology. So the question was, what happens if your event store crashes? What's behind this? Is there a DB behind that's going to save everything? What's going on? Because all we've really introduced is another point of failure. The event stores, we're going to talk about technology here in about 10 slides. But the event store is basically, at its heart, it's a log. It's just a text file that all you do is append. And that's it. And so there are appropriate technologies around that. You've got dual writes and everything. All that's wrapped up into this technology. They've got failover devices, things like that, multiple drives that it writes to. And depending on what technology you use, the three options are really Kinesis if you're into AWS, Event Hub if you're into Azure, or Kafka if you're into roll your own. We'll talk about that later. But you can depend on this, that it's always going to have your data. Once you write, you get an acknowledgement back. So you can write via HTTPS or various other ways, but you get an ACK back saying, yes, that was written, and then you can be confident that it'll be there. So, okay, so we're gotten to here, and now we've got all of our microservices over here. We scale as appropriate. If something gets hot, we scale it up. Obviously, we're in Docker. Hang just a second, I'll get to you. We're in Docker, Kubernetes, all those kind of cool words that we can use now. So Kubernetes is going to fire up more of these if it needs to. All that's managed by NetOps. But yeah, so everything is all fully scalable. Yes?
Who decides the sequence of like in which we are calling?
The events creation. So you come in here, the actor says, I want a t-shirt. He creates the t-shirt and then creates an event store, an order created event on the event store. I'm sorry, the question was who creates the different events? How do you keep all the microservices processing in order? And so he creates an order, and only this guy is listening for the order created event. So he gets it, he subscribes. This is a pub sub component. He gets that message or that event. He processes that, checks inventory, does his thing, and he creates another event saying order item inventory checked. This guy is subscribing to that. And so the dominoes just kind of fall after that. So you have to set up, planning your events is very important. You got to do that up front. Event storming, have you heard of that? Invaluable when you're coming on here, because you decide all the events that have to happen for all the different things, all the state changes that happen along the way, and each state change becomes an event. So, okay, so there is, if you're going full force microservices, you want this to be as scalable as humanly possible. What you would do is you'd also introduce a message queue up here. So the UI layer just creates a message saying somebody wants to create an order, and then it gets back to him and says, done. So now we're talking, microseconds right here. Our user's super happy. The thing is, messaging and events, when you transition from message-based to event-based, there's some weirdnesses that go along with that. One of the things that you have to be concerned about is how do you get your messages back? Say they're not allowed to create an order. Say something happens in here. How do we tell them, nope, sorry, you're missing information, things like that. So you can do a message queue, and that would make it ultimately scalable, because now this guy is also a microservice. But that's a whole other talk and how we deal with that. It is possible, you can do it, but for our purposes, we're going to stick with just having this be a small monolith. Is that even possible? A small monolith, and then these are our microservices. So now that I've filled you full of sunshine, let's talk about how this is not going to be the answer to all your problems. One of the hardest things that when you're pushing this through, so you're going to go to management, right? And you're going to say, I heard this guy, Brad, he is awesome. He's so smart. He told me all about this EDA stuff. We got to do it. He said something about eventual consistency. I don't know what it is, but it's fine. I'm sure it'll be okay. No. Eventual consistency, a lot of management, they think back to the time of data cubes, back 10 years ago when you had to dump a database overnight and you build this cube that was, 5 gig, which at the time was massive. And that takes hours, and the next day they can examine that cube and say, oh, it's not quite right, and they put back a request to fix it, and it's sometimes days or at least hours. This is not what we're talking about. Eventual consistency means that there is a short time when we've told the user their order is valid, and it may not be. But that's going to be like a second, 2 seconds, something like that. That's the eventual that we're talking about. So when you go to management and you say, we want to do this, has eventual consistency, whoa, not that. I can't wait that long. No, it's like a second or two. If one of your microservices goes down, something like this crashes, okay, our eventual is going to be a little bit longer. But happy path, we're talking a second, something like that, 2 seconds. But also remember that eventual, we don't really care. These are processing in the background. The user's gone. They're telling everybody the cool purchase they just made, their T-shirt. And so they don't really care how long this takes, as long as it's not days. So eventual consistency, you got to kind of push that through a little bit through management. Let's see, there is a minor impact on usability. So the user, if something goes wrong along the process, their credit card gets denied, whatever, they may get an initial message saying, yay, you got your T-shirt, and then 10 minutes later an email saying, boo, you don't have enough credit. So there is some user impact there. So you got to get product involved, make sure they're okay with that. But if you look at the big boys, Target, Walmart, Amazon, they all do the same thing. You know, you can buy something on Amazon and then get an email an hour later saying, oops, sorry, we're sold out. So everybody's doing that already. So it's the consumer is already in tune with that. They're already okay. And the devs, you guys are going to have to kind of change the way you look at things. It's a new paradigm. You don't control everything anymore. You don't have everything in your, I'm a Microsoft guy, so in Visual Studio or whatever it is, Eclipse, whatever it is you're using, you don't have all of your code all in there at the same time. All you get is your slice. All you get is your microservice. So you have to assume that everything that happened before was okay, and assume that everything that happens after is okay, and all you've got to do is focus on this. It's a bit of a paradigm shift, but it's a relief. All this stuff comes off your shoulders. Yeah? Who orchestrates it? So the question is, if one of your services fails and you need to start another one, who's orchestrating that? So all of this, we're kind of assuming that we're all running in Docker. Anybody Docker Kubernetes? Yeah. Wow, really? Does everybody know what Dockers and Kubernetes are? Okay, we got some no's. So let me touch on that for a second. So Docker is a way of containing applications on a server. It's sort of like, imagine a VM. You know, you can have multiple VMs running on one piece of hardware. Well, Docker is actually even a smaller size, where each VM shares the same operating system. So in a physical machine, you got an operating system. You've got multiple VMs, each one have their own copy of the operating system. In Docker, they all share an operating system, and they're just the slice of your application code and memory that the operating system uses. So it's a much smaller slice. So you can fit, physical piece of hardware, you can fit, let's just say 10 VMs. In a VM, you can fit tens, possibly hundreds of Dockers. So you've got everything running in Docker. Now there's another technology called Kubernetes that manages all of that, watches all these Dockers, because, we've got, even in our little system here, we have 3, 6, 9, 12. So we've got 15-ish already. And this is a small app. You could get into the tens or hundreds when you really build something out. So Kubernetes watches all this stuff, and it sees that one Docker machine is having troubles because it pings them. It pings them fairly frequently. You okay? You okay? You okay? And when one of them fails to answer, it says, okay, you must not be okay. Kill it, bring in a new one. So that's all the realm of Kubernetes, and basically, once you're in Docker, you don't have to worry about it anymore. And that's one of the beauties of Docker, actually, is you can imagine yourself in a single-threaded environment. You don't have to think about everything else, because Docker when you code for Docker, it's a little bit differently. You code as if you are the only user on that machine, because you really are. So you code single-threaded, typically. Obviously, you can do multi-threaded if there's advantages there, but the default can be single-threaded because you've got a whole bunch of Dockers there that give you the multi-threading thing for free. So if one of your services goes down, Docker sees it, throws in another one. Oh, sorry. Right. Oh, so you're saying our inventory system has checked that we have inventory. It puts as event store. Our financial system sees that, starts processing, and it crashes. How do we know where we left off? Okay, so there are a couple ways to do that. And depending on what technology you choose, Kafka, Kubernetes, or Event Hub, you can acknowledge these as processed. Or, so if it's that critical, you can do that. Or, and then if you don't acknowledge it, then it'll put it back on the queue saying it's unprocessed. There's a pointer. So every one of these guys has a pointer. All these three will share a pointer into the event stream. And so microservice 1 says, give me the next one. And your event store will say, here you go. The next microservice says, give me the next one. And that pointer is shifting because they're all sharing the same one. If one of them says, it doesn't acknowledge that it's processed its event, it'll go back in. And when the third guy says, give me the next one, the event store will say, oh, well, this, This guy never got back to me. Here, you can have this one. So you can do it that way, or you can manhandle it and go through and say, are there any event or any inventory checked events that do not have a credit card charged event, a matching credit card charged event? And just query. You can query these things, almost like SQL-ish. But you can query these things and say, if when your service comes up, you can say, is there anything that I missed? Typically what you do is there's you have an error checking process that runs hourly, daily, whatever you think appropriate, that does exactly that. Scans through and says, okay, we got these events. We know we did these things. This is our system of record. We know this happened. But wait, the next step never got processed. Okay, so let's pick it up here. Something happened. Answer your question? Okay. Yes. So the question is, do you have a trace ID? And yes, what you do is here, you put an original request ID. When you create this, that's the wrong one. We decided we weren't going to do that. So here, we put an original request ID in your payload. And so every event copies that original request ID throughout. There's no technical requirement to do this. It's just a smart thing. Otherwise, you get drowned in all the events and you can't tell what's going on. So yeah, you just stick a GUID or something like that in there and in a field called original request ID, and you can trace it through. So, okay, let's take one more, and then I'm starting to run out of time. And then we'll have to put a cause on questions.
In general, does event store has some sort of like system for throttling?
For throttling? So the question was, does Event Store have a system for throttling? No, because what it'll do is it's got a ping that's going here. And so there are two ways to get an event from the Event Store. You can poll if you want. Yeah, that's unpleasant. You'd rather get notified, right? But you can set up a ping here that says, are you ready for one? Are you ready for one? And when the ping comes back, yes, I'm done processing. Okay, here you go. And then you publish. So you code as if you were published to. You don't have to get a loop that's constantly polling. But you also implement a little API method that says, sorry, I'm busy. And so he's pinging you. Are you busy? You busy? Yes, I am. Sorry. And when he says no, okay, here's another one. So yeah, let's keep questions to the end because I'm starting to run out of time. I want to get to the good stuff. Still got some good stuff coming. So new paradigm for you guys. Keep that in mind. But it's kind of fun. It's fun getting there. So advantages. There are advantages all over the place for different people, different users, different things. So let's talk about them, kind of section by section. Advantages for the users. Faster response time. My guy up here is really happy, right? It got back to him right away saying, your T-shirt's on the way. Everybody's psyched. You can scale horizontally here. If this is getting stressed, you scale horizontally here. And just load balancer, typical scaling, stuff like that. Hopefully you don't need sticky sessions, but you can put them in. Just typical stuff that running a standard web app, but you can scale that out. User doesn't have to resubmit a failed request. We have all the information we need right there. If we crash here, yeah, he's got to resubmit that. If we crash here, no, he doesn't. We've already got everything we need. All we got to do is restart this, and we keep doing. So we've just, from the user's point of view, we've just cut crashes by 75%. Go to your boss and tell him that. Boss, give me this thing, and I'll cut crashes by 75% on day one. He'll give you the funding you need. Let's see. Request isolation requirements. Yeah, so that idea that it crashes 75% less gives them more confidence in the system. If you've got internal users, the system crashes like once a day. They're like, I got to use this thing again. Now it's only crashing once a week. Woohoo! Now we're all excited, right? The users think everything's going great. So it gives them a lot more confidence in the system. Advantages for prod. You can scale whatever you want, when you want. If this guy's hot, you scale him out. If this guy is, you scale him. You scale whatever. Kubernetes is watching all this stuff, so it's scaling automatically. NetOps is out getting coffee. They don't have to do anything anymore. This is all handled. Let's see. And the temporary scaling pressures is the real big deal. Say when Apple released their new iPhone, Can you imagine the servers going on? You know, they said, okay, the iPhone's on sale now. And all, boom, boom, all these people pounding on the buy button, right? So they've got demand that just goes through the roof. Well, Kubernetes starts having a heart attack and firing up all these Docker containers. But it gets handled. Everything handles. You know, you're still out getting coffee. So there are a lot of advantages to prod as well. Service failures don't affect other requests. So in our original thing, a service failure would affect other, say we had 5 requests going on at the same time in our application. You know, we're multi-threaded because we're good developers. One of our processes brings down the machine, brings down the VM. We've just lost all 5 of those orders. This way, one of them, we're in Docker, remember, so one of them brings down our Docker machine, which thinks it's its own machine. It doesn't affect anything else. In fact, we could lose everything. We could lose our whole backplane, and the user's still over here buying T-shirts. Everybody's happy. Well, NetOps isn't happy, yeah, but we're happy. Better fault tolerance. Yeah, we just talked about that. Reprocessing, so if something goes down, we can just restart it. We pick up where we left off. Let's see, advantages for you guys. Are there NetOps people in here? I don't mean to be slamming NetOps, sorry. Okay, good, all devs. We can slam NetOps then. Oh, no, I'm on camera. So the individual devs use, so like this gentleman over here was asking, we can code as if we're single-threaded. We can code as if we own the machine. That's so much better, right? It's so much easier to think that this is my machine and I can code that way. Let Kubernetes and Docker deal with it. Let's see. So we can replay event creation. Now we're getting into the good stuff. Okay, so if you're on your phone, put it away. It's time to really pay attention. Yeah, I see some heads popping up. So it's time to pay attention because this is the good stuff here. We can replay event creation. Say you're building a replacement because that finance system keeps crashing. That microservice keeps crashing. Or take this example, Christmas rush. You barely make it through Christmas rush, right? Whew, we're done. Next Christmas rush comes around. It's September. Everybody's starting to bite their nails and they're getting nervous. You fire up your event source and you rerun last Christmas rush. Just rerun the whole thing. Set the clock back because you can, that pointer that points to events, you can set them wherever you want. You can set it a year ago. Rerun Christmas rush and see if you can handle it. Rerun Christmas rush twice as fast because everything's there. You have a little service that feeds these and you take them faster than they really come in. Dial that up and see when your servers fall over. See if you can handle your rush. This is cool stuff. Let's see, you can recreate bugs. So you get a bug report saying when I do this, and push the button and kind of hold my head sideways, then everything crashes. You can say, okay, give me the exact time that happened. You go back in your event store and you set your pointer to 1 minute before that happened. And you fire everything up. You see what happens, right? You see the crash happen. Yeah? So you're asking if these need to be REST or SOAP or something like that in order for all this to work? Yeah, it's kind of one of the, you kind of do, because this is assuming that requests these are headless, right? This is just an API. It's sitting there. There's no UI. So there's got to be some way to get the data in. You can do REST, SOAP, MQTT, whatever you want. If you're IoT, you want to go MQTT because of lots of reasons. But whatever gets the data in there, something has to get it in. You have to have some sort of entry point, but it's not going to be a UI. And here's the cool thing. Everybody sees this, and they say, what? Test with production? You're kidding. No. This thing is write only. You write once, and you're done. You can never change that. So you can test in production. You write your new service over here, test with production data. Wire it up. you're not going to hurt anything. You can't hurt anything. As long as you've got your own database, your own service, running in test or QA or whatever environment you want, grab these events and see if you can handle it. See if something comes through that you're not expecting. So you can test in production. That is so cool. Let's see, advantages for the business. Before we had one source of truth that could be changed. So somebody comes in and says, ooh, that user really shouldn't be there. I'm just gonna fix that, right? And they issue an update query. Our one source of truth is now different from the truth that was yesterday. Here, no, sorry, once it's in, it's in. This is more like a financial record. If you put something in by mistake, you have to do a reversing entry. So you can't just go in there and change that thing. This is set in stone, and that's the way you want it. That is the truth. That really happened. It probably shouldn't have, but it did. So you got to go in and fix it. So one source of truth. Well, you get in when you something that's handling an event or writing an event. You create an event saying inventory check failed, and something else is that's the eventual consistency, right? She's saying, what happens if your credit card fails, your inventory fails, one of these services fails? Either fails appropriately, like checked your credit card, sorry, you don't have enough cash, or fails like it crashes. If it fails appropriately, you don't want the process to go through for some business rule, then you create an event here saying order failed, credit check. And you've got another process. Maybe the notification system is watching for those events. It sees that and sends out an email saying, oh, sorry, you don't have enough credit on your credit card. And then the whole process still finishes. It fails from the user's standpoint. They don't get their T-shirt, but it succeeds from the business standpoint because you've successfully completed the process. If a microservice fails, then we've talked about that, right? You can detect it by querying this guy. You can detect it various different ways. And so the business process should always succeed. Whether that results in a success for the actor or not, for the user, depends on business rules. Yeah, one last one, and then we're running out of time. Yep. Yes. So he was saying that you have to have a general business agreement that these events accurately reflect what the business really wants to have. This is a state machine. The things that process these events are state machines. They check to see that the state's in a certain way, and if so, they need to take action. And so, yes, you have to get the business and the developers and product and everybody to agree that this is how things should work. That's where the event storming comes in. Look into that. I mean, it's a great process. Alberto Brandolini leads that. That's really good. Okay, so I'm going to have to rush. We got 11 minutes, and we're running out of juice here. Enhanced planning for the business. So the business can come along and see exactly what happened last year. Christmas rush. They're up there planning for Christmas rush. Businesses, the CEO's getting nervous, saying, oh my God, can we handle how many did we sell last year? You're like, query my event source. Okay, we had 16,000 orders per second last year. And now we just finished a test that says we can handle 40,000 orders per second. Okay, CEO's happy. And if the CEO's happy, you're happy, right? Right? Okay. So yeah, you can analyze things after. You can analyze the time, because each one of these events has a timestamp. So you can see, are there blips? Is there a certain time of day? Marketing, you hire a new marketing manager, and he says, your stats are terrible. I need all this other data. And we say, okay, we got it. Go through our event store. We know exactly when orders were created, time of day, down to the microsecond. And so he can analyze, what time of day is good for t-shirts, what time of day is good for electronics, stuff like that. You can come in after the fact, and this is the real business idea that I'm trying to get to. You can come in after the fact, have a good idea today, and use yesterday's data. You don't have to have a good idea and then go collect all the data, right? You can figure it out today, say, wow, this would be cool to know. Go back in time, go back 2 years, collect all that data, crank out all your numbers, and prove that your idea is good. Domain decoupling. We all know this is a good thing. So fast responses to changing market. If all you're working on, the microservices, I've heard so many different definitions of what a microservice is. How big is a microservice? Micro means is like this, right? Not really. Something that I've heard a lot of good definitions. Something that I try and keep in mind is a microservice is small enough you can keep it all in your head at the same time. So if somebody asks you a question, what does it do in this given situation? You know. And in an application I'm working on now, we got 2 million lines of code. Somebody says, what happens when in this situation? I don't know. I'll get back to you in a couple of days. Let me go dig in. So with that in mind, fast responses to a changing market. So product comes to you and says, I need this new feature. It's going to be awesome. You can sit there and think, okay, that's probably a 2-sprint thing. And you can tell them right there. And then you can actually deliver. You can actually deliver in 2 sprints. So you can break things into smaller domains. Microservices are smaller. It's easier to add features to smaller things. Better error recovery. We've kind of gone over that. You don't, let's see, you can go back and retroactively reconstruct your data. You can, if you know the time that you got the exception, you can go back and rerun those events for that 10 minutes and reconstruct your exception. You can release special customer features. So you can have a service over here that says, if an order is created for this particular vendor, for this customer, Nike wants some super special marketing numbers. You can say, if this is a Nike order, okay, we got to handle this specially over here. And you, again, go back in time. Nike wants this data starting 6 months ago. Go back in time. So that's the promise. That's the theory. Goodsized Downside. So here's some practical results. This was Gilt. They've got about a 150-person development team. You can see the progress there. They moved to microservices. They started out with a monolith, started migrating to microservices. And you can see here towards the end, this is developers versus number of microservices. And you can see that just skyrockets here. The red, it's hard to see. Red is services, blue is headcount. And so they were kind of parallel through here, and then the number of services, as they figured it out, it just skyrocketed. They've got thousands of Git repos, 1 repo per microservice. And they're handling a ton of requests per day. So all this is on the web. So look up Gilt and you'll find these same numbers. You can find them for Target too. I mean, they did the very same thing. They've got all of their dev is done in APIs now. They have very, very few UIs. Time from code commit to production decreased by 20% because they're pushing so much faster. This is their overall view of their retail. They've got all their supply chain APIs down here. And basically, one thing to keep in mind is data duplication is a good thing when you're talking microservices. You listen to all these events that you care about, and when an event comes in that's something that you care about, you can't change the event, because a different domain manages that data, right? But you can say your inventory system sees that a new order comes in. If you care, you can cache that order in your own domain. Every time a new order comes in, you cache that data. Now you have a copy of the orders that really belong. You're not allowed to touch them, but you can hit them, you can read them very quickly on your own without having to go over an API to the order system. So data duplication, when you're talking microservices and EDA, data duplication is okay as long as only one is changing it. If you have two services changing the same type of data, the same data field, now you're going to get yourself into trouble. But caching read-only is fine. Yeah, and these guys are on 70 million visitors a month. Who's got 70 million visitors a month? Yeah. Wow, do you really? Holy cow, we got a hand up here. Let's talk after. Okay, technology. How do we do all this stuff? You got a couple options. If you like services, if you want somebody else to handle the grunt work and you just plunk down your credit card, you've got Amazon or Azure. They both have excellent solutions, Amazon Kinesis or Azure Event Hub. They're basically the same thing. There are different features, little tweaks here and there that each one does better or worse than the other. But you can look at both. They're easily turned on. They're available in about 5 minutes. They're fairly inexpensive. It's not as rich as Kafka, but it does the job. If you're doing POCs, proof of concept, either one of these is fantastic. This is the way to go. I think they even have free up to like 1,000 events a day, something like that. They've got different decent usage scenarios like that. If you're more of a roll your own, Kafka. It's more advanced. The querying features are more advanced. They have this cool thing that their query language lets you create a query that's then a moving window. And so it basically creates a data set that's constantly updated, so the results of your query are updated in real time. It's more like a filter, I guess, really. They call it a query, but it's more a filter. So, but these guys, they're kind of a pain to manage. You need they recommend Kubernetes of at least 8 nodes. They have they have a specific structure of the Docker machines that they use. You need NetOps that are competent. But it's a good way to go. It's an excellent technology. Just if you're doing a POC, do the same. The Azure or AWS, whichever one you want. Let's see. Or just recently, I haven't had much of a chance to look at this yet, but just recently, Amazon is kind of doing the same thing with Dynamo. They've got something where if you're using Dynamo already, it will create the events for you. It'll see the updates that come through and create an event just on the changed data. So it's kind of cool. It's a cool idea. And it's convenient if you're already using Dynamo because you just flip a switch and it just kind of happens. So, but like I said, I haven't checked that. I read the marketing. It sounds promising. If you're already on Dynamo, you may want to look into that. Let's see, and that's pretty much it. We have about 3 minutes if anybody wants to toss out questions. Wow, holy cow. Okay, we've done a lot in the front. Let's go in the back. Yeah. I'm sorry, I can't really hear you. Yes, these are event stores, and they're just plug and play. They give you an endpoint, you write to that endpoint, and you're done. The event's there. They give you a different endpoint for reading, different endpoints for filtering, that kind of stuff. But yeah, they're plug and play. You turn it on, plonk down your credit card, and you're ready to go. Yep.
It looks like that the event store becomes a single point failure for the whole system. And it basically, what happens when, what the scale is like, it also becomes like a bottleneck, right? Everything has to come through that, so how do you deal with it?
So the question is, doesn't the event store become a bottleneck? Now it's a single point of failure. So there are 2 questions buried in there. Single point of failure can be handled with various normal network technologies. You've got failover servers, you've got failover disks, write multiple times, all those kind of things. So, and with Kubernetes, it's shutting down Docker, creating them, those kind of things. So they've addressed that with those kind of technologies. And there was, single point of failure because of, what was the other? Throughput. So, and actually this is really interesting. I need to add this slide because Kafka published some numbers. Throughput from day 1 is exactly the same as throughput from day 1000. because all they do is write. So they're writing. It's just an append log. And so event creation is just the same as you're out here. Typically the events and so that's writing. The write performance is nearly exactly the same because you're always writing to the end. The disk head is always right there, right? When you're reading, normally you're reading something that happened within the last probably couple seconds, typically is what you're doing, and that's all still in memory. So the reading is pretty good too. If you reset your pointer back for a little while, yeah, you're going to have a little latency as the disk heads move back to where it needs to be and comes back forward again. But they've optimized the memory so that it keeps as much in memory as possible, and your reads are usually just, they're coming out of memory. And so all you have is one write going. The performance for Kafka, Kinesis and Amazon or Azure haven't published any numbers. I assume they're roughly the same as Kafka. I mean, they're bright people in Amazon and Azure. But it's incredible. Get on and Google the performance, and it's like within 1%. The 1000th day is within 1% of performance of the first day. Yeah. Wow, that's like 7 talks right there. The question was, how do you know when you're not overdoing your microservices? Yeah, that's a whole nother, here, take a card. Yeah, give me a call, we'll talk about it, because there's all sorts of things going on in there. Let's get here, and then we'll come back.
Okay, you keep appending to this block, eventually you're going to fill up your disk.
So you get another disk. Right? You throw another disk. I mean, Target has like 6 years of data. They've got, God, I don't know, 50 terabytes, something like that. It's just massive. The guy, I went to a talk by the CTO of Target. It was really informative. If you ever get a chance to see that guy, it's a really good show. But yeah, he says that the thing is just massive, and they just keep adding disks to the end. They just add disks to the end. They reread the whole thing so infrequently that it's not a big deal. So they understand there's some latency. If they want to go back 6 years ago, yeah, they may have to go sit and wait for a little while. But if they want to go back 10 minutes, it's still in memory. So yeah. So the question is, if multiple things are writing to the event source, and you're processing one and a new one comes in, you're saying that that's a conflict? Right. Yes. Right. Yes. So the question is, if you want to break, say you've got one microservice that's starting to get overloaded, there's too much, it's basically 2 domains. It's time to chop it in half. Yes, you're going to have to create multiple events so these 2 microservices can converse. But that's part of the process, right? You're going to do your event sourcing. You need to figure out why these 2 are different domains, what responsibilities do they have, and how to make them communicate. But so the question is, so we've done this. We've broken our domain into 2. Now we go back and try and run last year's data. Well, remember, we're on Docker. Docker has versions. So to run an event, to process an event from a year ago, you pull the proper Docker and process that event. And when your domains get chopped in half, now you pull those Dockers and process that. So you can, assuming you're keeping all your Docker versions, which you should, you can process back in time and actually process, as if it were production. typically, if you're going to go back in time like that, what you're doing is you're trying to test new stuff, and you go back. So yeah, you have to keep that in mind. There are points where it's going to be difficult to go back in time and reprocess. Yeah, you're right. But there's not much you can do about that. Sorry, guys. For more questions, why don't you bring them forward? I don't want to. The next guy's going to come in and has to set up. So why don't you come on, bring it forward. Thanks, guys. What's that?
Can you get your slides?
They are. Oh, slides are on SlideShare.
SlideShare?
Yep. Yeah, just look for my name on SlideShare.